Good evening to all of you. Welcome to the second session of this 11th day of faculty development program on shallow and deep foundations, being organized by the Department of Civil Engineering, Andhra University College of Engineering, under AICTE Quality Improvement Scheme. So in this session, we have a lecture by Professor G.V. Rao on the topic of geosynthetics in bearing capacity improvement of soils. So though the title is given like that, I think Professor G.V. Rao will expose you to various geosynthetic products and their applications for both shallow and deep foundations. He will touch upon, I think, strengthening of soft clays using geocomposite drains and all, right? Strip drains and all. So anyway, I hope this lecture will be more interesting and useful to your profession, particularly for practicing engineers and for those who are doing research, right? They will also get some new areas where geosynthetics can be used, right, in soils for improving their strength and stiffness, right? So during morning session, as pointed out by Professor Madhav, you can think of preparing reinforced soil beds to support footings of moderate loads on soft soils, right? So the reinforced soil bed itself is designed to take the significant stresses from the foundation, and underlying soft clay is not overstressed. So anyway, I thank Professor G.V. Rao sir for supporting this event. So you have already listened to him through several lectures, right? So in fact, he has delivered the inaugural lecture for this FDP, and again he is taking up this lecture on geosynthetics, right, for both shallow and foundation applications. So I invite Professor G.V. Rao sir and request him to deliver his lecture. Please, sir.
Thank you, Professor Garu.
Sir, I am stopping, sir. You can stay.
Yeah. Good afternoon, everyone. Am I audible? Hello?
Yes, sir, you are audible, sir.
And the screen is visible?
Visible, sir.
So the outset, I am grateful to Professor Satyanarayana Garu for having given the opportunity to
Yes,
me
sir, you're
from the initial lectures and also for the final lecture. I may disappoint him in the sense that I am not going to cover all the aspects which you mentioned, because geosynthetics is a very vast subject actually. And as you know, there is a wide variety of materials which are there. There are geotextiles, which are could be woven or non-woven material. There could be geogrids, which are again of at least two fundamental varieties: the uniaxial grids and the biaxial grids. Then membranes, then various kinds of geocomposites, and then of course many other materials which are necessary but may not be consumed as much as the earlier four varieties. Now we know that all these materials perform five basic or primary functions. That is separation, which means that it is separating two dissimilar geotechnical materials. That means, let us say, when you're considering pavement, obviously, it is if you are placing over subgrade now, it is not going to allow mixing of the fine subgrade soils and the pavement material. In the same way, it may allow drainage to happen along the plane of the geosynthetic, which would be a non-woven geotextile. And then filtration means flow across the geotextile, which could be mostly non-woven material, which allows only the water to pass through, but not the soil particles. And then reinforcement. Now, reinforcement is one of the most common topics which is dealt with in reinforcement, in the sense that in geosynthetics, we are doing a lot of reinforced soil walls today throughout the country, um, for walls and for slopes and for basal reinforcement and many other applications. And the last application, the last function is mainly moisture barrier. That means it will not allow water or any gases to pass through that. So moisture barrier is a function performed by geomembrane. There is also one more secondary function you can say. It will allow us to have a cushion. That means, the moisture barrier material, the geomembrane is not very strong by itself. It only barrier basically. So in order that it's not affected by construction or any other damage actually, we place a cushion of a non-woven geotextile on that now. So that means protecting the geomembrane actually. And these geosynthetics have got applications in, I should say, every conceivable field engineering aspects. And most of you know that I have written a lot of books on that, collecting much information, right from landfills to many other applications actually. And those who are interested, you can watch the series of videos available in iGrip, I small and G capital, iGrip site at the IIT Gandhinagar. There are about 40 lectures, most of them given by me and also experts on subject now. You will find a lot of information on that actually, and many other videos which I have been preparing for the last few years actually. So I'm not going to cover all the aspects now, but I will cover the specific aspect. Of course, we'll go around slightly. So what I try to do, of course, is that at IIT Delhi, we started working on subject since 1985. So since 1985 to for the next 10 years, actually, we've been trying to understand these materials, the various kinds of materials, as I mentioned, the woven geotextiles, the non-woven geotextiles, and the geogrids of different kinds, and many other things we have been trying to understand. And several PhD materials have come out of that now. And at the end of that 10 years, more or less, we felt that yes, we're able to understand it, but we're able to make a significant impact now. Either we need large facilities, which require a lot of investment by the project authorities, which was not naturally coming forth. So I thought we should try to get into the practice of the subject now. How can you practice the concepts which you understood and which are already standardized by the British standards and the American standards? And so a lot of applications have been actually developed in the state of Andhra Pradesh, firstly on soft soils. And so I thought that actually I will initially, for the first one third of the lecture, I will try to give you those aspects which I understand by the laboratory work to begin with, maybe sometimes the actual work, sometimes the model tests and things like that now. And then, of course, we try to give you one major example of its use actually on a soft soil now. So when you try to look into that now, whenever we have a kind of soft soil and we want to improve that, let us say by placing a granular material over that now. So this is a granular material. If you think of pavement, naturally it will be sub-base kind of thing. But then normally also we know very well that we can't construct foundation on a soft soil directly because foundation ready to sink now. And so we always place a little granular material. So when you place a little granular material, even that may also start sinking into the ground. And in order to prevent that now, for example, we can now place a geosynthetic. That means first on the uh, foundation soil, on the soft soil, we place a geosynthetic. And then, of course, we construct initially some granular layers. Now. Say, let us say that something like 15 centimeter granular material. Now. When once you do that now, what is likely to happen is that whatever load is going to come, whether wheel load or any other load which is going to come foundation tomorrow, so that will be first dispersed through this sandy soil, let us say, granular soil now, and naturally it will like to spread because it is going to be spreading like, as you know very well, how it's going to spread in a foundation now. So when it's trying to spread now, naturally it becomes, if there is no geosynthetic here now, it is allowed to move freely. So that means it's going to cause punching failure or blockage failure, but that is prevented by actually replacing geosynthetic now. So when once you place geosynthetic now, it is not allowed to move by itself onto the soft soil or into soft soil. It will generate a friction actually. So by generating friction now, it's like the other way around. It's giving a lateral restraint on the system now. That is most important now. So that means the soil which are made, some granule soil now, is being confined to this area just below the expert foundation or V load, as the matter was. So that load, whatever load, compressive load is reached now by virtue of the friction at the interface actually. So that is the cause for all our efforts now. So basically, we know that we are all dealing with compressive force only, but then by virtue of the attempted movement of the particles over that now, over the geosynthetic, naturally we are going to spread, we are going to cause a tension material. So this tension which is going to cause lateral restraint. Otherwise, tension is not in the structure. It's all compressive loads only. So please remember that now. In addition to this, we can throw clear into this any excess pour-out pressure developed the application of this load now, that pour-out pressure, excess pour-out pressure can be dissipated by the filtration and drainage aspect of this geotextile actually. If it is got a non-oven kind of thing, it will allow to filter now, that means only water can go through and not the soil particles. And then also along the plane of the material, drainage function now. And of course, if it is a strong geotextile, like oven geotextile or a geogrid, we'll see more of geogrids also later, and it's going to give us much more lateral restraint. So this is a first hypothesis placed before us to understand in what manner the geocentric is going to work. The other way of trying to look at it is now, we can look at the same kind of phenomena. That means we got a load here, and then we got a layer of a layer of geocentric now over a soft soil. And normally, what's going to happen is we know very well that it becomes two-layer theory now, and the influence of soft soil is going to be felt very, very heavily now. Once you place the geosynthetic here, actually, what's going to happen now? The the failure wedge actually, or the failure zone basically, is going to intercept the geosynthetic now. That means this also is going to come into picture now. By this process now, if our earlier failure zone is going to be limited to the dotted, because actually it will increase actually. The actual failure zone is going to be much wider, sometimes deeper also, than the original one now. That means more soil is participating, more granular soil is participating in the load distribution now. That means obviously the stress on subsoil is going to reduce now. So that is what we call as, that is what is the cause of a bare capacity increase. And we see, well, all aspects which are going to see later, that this increase can be even 3 to 10 times also. So a lot of our students have done work on that. I will illustrate a few things actually. And if by any chance there is more sinking also, the advantage of all of them is, I mean, of course, in a pavement there's a rutting, but here we're not talking about rutting. I mean, earlier we just thought that we got this kind of system now. So if this is going to cause, let's say, settlement by some chance, okay, which is naturally happening if the material itself is initially not capable of doing it. So by its process of having this curved shape now, what's going to happen now? The geosynthetic is going to expand, is going to extend. And once going to extend now, that means the actual strength of the geosynthetic is going to come to picture now. So its vertical component of this actually is going to act. This vertical component I am showing you, that is going to resist the load now. So that means this vertical component resist the load means the pressure beneath the geosynthetic is going to reduce. That is a great thing actually. Now this can happen if it is a pavement naturally under two wheels, and if you got a let us say individual footings, many number of the neighborhood naturally, the entire thing is going to act a membrane. That means between one column, other column also, it will act like a tension member actually. That is the beauty of it. Now, these are the three hypotheses which have been given out over many years, and these are hypotheses to understand better now. And it's not possible for us to actually develop equations for this. That means there is no solution for this basically by these concepts now. It helps us. That's why it's called three fundamental hypotheses why this strength is going to increase. The other important thing is, of course, we go to embankment and soft soils now. We spend a lot of time on that today. What is really going to happen is now we just assume that let us say an embankment is there now. The embankment is resting on the soft soil, that is the foundation, basically foundation soil. And just for understanding only, we put a difference between these. Also, they are different elevation. Actually, this is in contact only. So once that is there now, what is going to happen now? This embankment you have to move, and the resistance is going to be there at the bottom now. So that is coming out actually by placement of again geosynthetic here now. So geosynthetic is going to resist this movement now, and this has been very well used actually because the footing subject outward stress now, and this inward stress is going to develop actually by virtue of the geosynthetic now, and by the process we see that now this friction, as we thought a normal case now, like Vasil's case now. So I have shown you this Vasil case also how we considered bearing capacity of a rough foundation. So here, if you got a grid now, this is going to be taken as a very rough foundation now. So what's going to happen now? Our earlier well capacity factor NC was only, I have mentioned to you earlier also 5.14. Now thus keeps increasing actually. So that is the main thing which is going to happen now. Bearing capacity factor is going to increase now. And naturally, because outward this one now, if it is going to smooth now, it's the other way around actually. So this aspect we will have to really see in a big way. So same thing is going to happen in this case also. Sorry, it is missing now. But the bearing capacity factor, I mean this side is bearing capacity factor now. And you can see that there is a continuous increase in the bearing capacity factors depending upon the shape and size and everything else which is there. So by this process, we are going to think now. We are not talking of only normal building foundations. Mind you, I am just talking of general foundation cases now, which are which is feasible to take up the improvement, ground improvement, without necessarily a change in the settlement. That's the first thing we are going to look at. So once you look at that now, in this case, what's going to happen if you start constructing very fast? If you start constructing very fast now, what's going to happen now? The bearing capacity, the factor of safety against failure is going to be obviously decreasing. Initially, it could be more than 1 now. It will keep decreasing. Of course, this hypothetically shown, but it decrease at 1 and it fail also. Okay. And just before failure, if you stop it, what's going to happen now? Naturally, the excess water pressure generated in the soft subsoil actually is going to slowly dissipate, maybe by virtue of a sand layer here or much below this now. And what's going to happen now? Naturally, when the excess water pressure is dissipated, the soil itself is going stronger now. So its value of strength is going to improve now. So what's likely to happen is the side factor is likely to increase. On the other hand, now if you are going to place actually geosynthetic in the interface with embankment and the soft soil now, the major so now, so the factor of safety is not going to come down below 1. It will come down because the power pressure has been generated, but then it will always remain actually more than 1. So that is a classic case now. That means the geosynthetic is holding forth till the bearing capacity, till the strength is improved by the dissipation of excess forward pressure. That is the main situation we are going to do. We are going to come. So in a conventional, we can say reinforced soil applications now, what is going to happen is the wall or the reinforced slope, the reinforced wall or reinforced slope actually is designed, let's say for 100 years, 100 years creep also. So by that process, what happens is now the strength they are going to determine in the laboratory, the short-term strength, the ultimate strength of a geosynthetic now is, let's say, value X now. Now we have to apply a lot of corrections to this for damage during construction, which is installation damage now, due to maybe changes in the material itself now. Lots of things can happen now. But one most important thing is that because plastic material is going to creep now. This creep is going to be high, obviously, at high temperature zones like in the south of our country, and naturally, and low temperature zones like Kashmir in our country. So what is going to happen is now the creep is going to be significant phenomena. So if you combine all these factors, actually, the design strength of the material is likely to be almost 50% of the ultimate strength. Now, that creep part of it is not required in this case because this improvement occurring by the drainage of this water is going to occur very shortly. And so, the actual design strength is going to be very near that of the ultimate strength. That is the important point. So, that means when that is going to be the case now, we are almost able to use the full strength now. That means it's going to become cheaper. Is going to become less expensive than its use in a reinforced wall or reinforced slope now. That is the beauty of this entire thing now. Because after the total effect, the total excess forward pressure dissipated now, the soil becomes stronger. That means the soil itself, without the geosynthetic, can take the load of the embankment. That is the main thing actually. So that means the geosynthetic is going to become redundant after the dissipation of the forward pressure. So that is the main thing now. So there are many theories for doing it now. I will not want to get into all things now. But what is really the principle is if you try to plot the stress or actually principal stress, compressive stress actually, one pair is going to be drawn here now. The alpha and beta planes actually as they call conventionally. So if these are the compressive stress planes actually, alpha and beta curves now, what is it you find? You find that in this zone now, it is compression actually. In this zone is compression. And whereas extension is there, is a tensile arc actually. So that means any zone wherein tensile tension is there now, if you place a geosynthetic there, naturally the geosynthetic is going to take care of the tension. So fundamentally also placing a reinforcement below at the interface horizontally is always going to help us. That is what is shown here now. It's going to help us a lot now. And then when once naturally the edge is going to come now, these planes are going to move vertically. So what is going to happen now? Naturally, we need reinforcement which is going to be placed vertically. Now it's always possible for us to put a pile or something else vertically, so no worry at all. But then you can't place it horizontally. This can be only done before construction. Now, this kind of things we can do also in case you don't use any technology, but there's a failure which you didn't anticipate now. We, in India also we put a lot of bellies, a lot of poles, a lot of pipes, and so they're going to stabilize. So fundamentally, it's the correct thing that away from the toe of this embankment, we need reinforcement vertically, more or less vertically, and then we need reinforcement which is horizontal at the interface of the soft soil and the embankment actually. So that is the most ideal state actually by theory also. So that is what we are trying to do. So we can see some examples of a geogrid basically, how it's going to function now. And a lot of workers have done work now. Quite a bit of work was done. Professor Madhav has shown you by Venkat. That was essentially using metallic strips. Now, Professor Das and his co-workers have done extensive work on the subject of placement of geogrids, how it's going to influence the bearing capacity. Mind you, in all the cases, its bearing capacity is going to improve now. We are not going to touch upon the settlement. If you want to take settlement, there is a different way. We'll see that a bit later now. So what is going to happen in this case now? We can place as a first level at the interface between soft soil and the stronger granular soil now, which is the usual fashion we always do. And by placement now, a lot of theories we can work out exactly like our classical theories now. So what is it which you find is now that this zone of failure actually in the stronger granular layer is going to normally something like this. It's going to go like this. So once you place this geosynthetic actually or stronger material in general, so naturally the zone is necessarily doesn't have to be strong now, but then this is because of the stronger granular layer is going to be influenced now. So that is a classic case now. So how do we make it stronger now? Naturally we make it stronger by placement of a geosynthetic at the interface or of course within the granular material also. That makes it basically the same material but improved further by using a geosynthetic now. Before we go into that, one of the classic examples of this was done by Professor Lee long ago, almost 3 decades actually. He has done a wonderful experiment by triaxial testing in a laboratory itself. Now, what he has used is he has used a sand actually in a triaxial test, very low confining pressure, and then he conducted a triaxial test. On the x-axis, we find the strain in percentage. On the y-axis, we find the axial stress, not DHS, total axial sigma 1. So he has actually used a normal sand, and in that sand now, if you conduct the test now, this is the kind of stress center we got now. On the same kind of sand, at the same density, he used wood waste, wood shavings, Our carpenter, when he wants to plane a wood, actually, we get the shavings kind of thing now. So those wood chips actually are so thin, 0.008 inches in thickness, and then width is about 0.05 inches, and then length is 1 to 3 inches. So such a kind of material, waste material, just 1.2% by weight. Remember that just 1.2% weight he placed in the sample actually in the specimen of sand, and then he got this kind of curve. This is one of the most wonderful pictures I remember always classically. Now this picture shows the 3 things now. Obviously, in this case, it is a loose kind of sand. And then in this case, we see that it is behaving almost like a dense sand actually. So you see this value of the peak value is almost in the whatever in kg per centimeter square, 1.2 kilograms per centimeter square. Whereas here, what is the peak now? There is no peak at all. It's almost flat only. It's 0.2. So what is the increase in strength now? 5 to 6 times the so-called peak strength is improving now. And here it is reaching a residual state. Here it's not at it. Still around the peak only. And what about the slope of this now, the stiffness of this? That also is improved now. So 3 things happening now, that the peak strength is definitely higher, residual strength is much higher than the peak of this unreinforced material, and the initial slope of this now, the elastic modulus of this is going to be much higher in a reinforced system. And by using any kind of material, it can be this kind of waste, any kind of waste now. And mind you, when we say the place in the waste now, it is actually becoming kind of isotropic behavior. It's a kind of isotropic behavior because we are placing everything differently. On the other hand, our students at IIT long ago have done a lot of project works and which also on the subject. So in this case, what we have done, we have taken the local sand and tests were done in a smaller scale also. That means 37 mm diameter samples and later 100 mm diameter specimens also. and we place actually disc of this now. That means whatever is diameter of the specimen, we place the same diameter disc actually. Number of them, for example, we can place up to 8 also. And we tested this at many confining pressures. Okay, so if you just look at the the what do you call the curves which are marked 0.5, 0.5, 0.5. So what is it which are trying to look at is actually this is again the actual strain versus the deviated stress in this case now. So the result is being shown clearly that 0.25 is the curve actually with no reinforcement, and this 0.5 means one discrete reinforcement, and this means another two kind of thing. So we find that actually there is a subtle change definitely. There is so much improvement which is occurring in this. Okay, so whatever I said earlier, the scale is small here, so that's why we're not able to show this. So we find that at 0.25 it's much more also actually. The improvement in strength we find is not so significant when you go to higher pressures also. When you go to higher pressures now, we find that it's not going to be so effective definitely. Why happening now? At lower confining pressures, we find that the effect is going to be dominant, and when you go to higher pressures, the effect is less dominant. Now, what is the purpose of this now? This is what we say Mother Nature. So if you are weak now, reinforcing is going to improve your strength. If you are strong now, you don't need reinforcement at all. So in a stronger sand, actually, in a dense sand, we don't need this now. In a weaker strata, definitely we need this now. So the behavior, as I told you, becomes from earlier loose sand to dense sand kind of behavior. So same thing is shown here also by different kind of testing also. In this case, we have placed 1, 3, 5, 7 candidates now, and we are seeing the result here at 25 kilopascal confined pressure and at 400 kilopascal confined pressure. So the kind of thing we are trying to see is that now, yes, the strength also improves, the overall behavior improves with the number of reinforcements, and then here also it improves, but then the extent of improvement is not going to be as dramatic as it is. Suppose here applied 400 kilopascals, let us say it's about 1.3 or something, 1.3 to maybe 2.2 or something. Here, what is happening from say 0.1 or something like that to almost 0.5. So the effect is always felt much higher at a low confining pressure and then at a higher confining pressure. And also, if you keep on adding now, the initial effect is always more. That means placement of one or two is going to be more effective than placement of a number of them now. So, and also, of course, a lot of results must have been shown by Professor Madhav also to you, where to place it now. If you are going to place this adjacent, very near the foundation, naturally the effect is going much more. All of them are really done now. So, when you try to summarize all the results in this case now, this very interesting picture now. So, we plotted the sigma 3, the you can say manipulation stress or the confining stress actually, and of course the vertical stress actually. Okay, vertical stress to failure. So if I try and do that now, on this axis, what is it to find? On this axis, we find that this is the line for pure sand only. And then the next line is for, let us say, one disk, and then 3 disks, 5 disks, 7 disks. So what is it you are finding actually? If you just go vertically at the same 200 kVA confining pressure now, we find that the strength significantly improves from, let us say, 0.8 to almost 1.6. Okay, if you go horizontally, let us say for this now, but in entity level, suppose you go to horizontal 1.6 to this one now, what is happening now? The strength is here naturally. What is the strength here? The strength, whatever value is there, is being obtained around 350 confined pressure, 370 confined pressure. Whereas the same strength is obtained actually at a much lower confining pressure. That is the beauty of it. So that is why we call this change here as naturally responsible for giving this now. This is what we call as apparent confining pressure. So though we are applying same confining pressure now, the strength values, certain parameters are going to be much higher than unreinforced case now. So that is why it's called apparent confining pressure now. So it causes apparent confining pressure. Mind you, this apparent confining pressure is there so long as the sand is there or so long as the soil is there. Why I am doing this now? If you try to have this foundation near let's say river or canal something, which is to score now, naturally if the soil is removed, naturally effect of foundation movement is not felt also. So the soil is as much component as the reinforcement now. So that is what we have to always remember this now. So this behavior actually has been examined in many different ways now. Our students have done with different kind of materials, reinforcement, different kind of confined measures, and also with payments of materials in a big way. So all of them actually point out the behavior is almost like this. Okay. Like this, what I meant was it is going to be something like a bilinear behavior. Okay, what do you mean bilinear behavior now? So beyond some level actually, beyond some confining pressure, you see this failure envelope actually is parallel to the unreinforced case. So beyond, let us say in this case 100 kilopascals now, the strength by any number of reinforcements is going to remain actually with this pi value, but the C value, the apparent coefficient is going to be definitely increasing. Initially it was 0, and let us say at 7 days now it is going to be of the order of about 0.7 or 0.65. So that is what is going to happen. So phi is going to be constant, and then C is going to increase. That is a model I liked it. So a lot of our students have done work, and we have published a lot of papers on that also. So any kind of case pick up now, this is what is going to happen with the geotextile or the geogrid or with small cut piece of materials, and all of them is going to be same now. So similar kind of work has been done actually with micro mesh also. That means, we can take geonet, cut into pieces of different lengths now. Same general behavior is going to form actually. So again, as I told you, in this case, the percentage of the mesh is anywhere 0.24 to 1.4% only. These curves represent what is happening at 50 kilopascals confinement pressure. These shows at 20 kilopascals, and like this, it is at 100 kilopascals. So behavior is going to be more or less the same kind actually. The only difference is whenever the cut pieces are in waste material, the behavior is going to be isotropic, otherwise anisotropic only. So that means so long as it's there, it is a vertical is going to increase, not anything else now, and behavior will not be shown in the lateral direction now. So these values are available and published literature by us actually. So as I said, more than 100 now for a given system of sand and reinforcement now. So let us say the phi value is, I'd say more or less same, but the C value is increasing significantly. You can see this 9.6, 115, 146. Okay, less than 100 kilopascals confinement pressure, I am shown also. C dash having 0, and this is increasing systematically. Okay, so both are different in the direction now. It's all based upon what you call as what you define as critical confinement pressure. This is just to illustrate now what is the phenomena. So a lot of results are published actually. And then we said, what is the publishing all this information now, unless related to actual condition. So we took some kind of theoretical models now, in which we said, okay, we got a clay of known strength, and then we put a foundation and of width B, and naturally this is at a depth of the foundation depth is df now, and the sand layer actually, the normal sand layer is h, thickness is h now, and this is what we replace actually. In this case, normal, it's not normal sand compared to sand also, and the geogrid micro mesh reinforced sand. So if you are trying to look at that now and compare the bearing capacity values which you get by bilinear theory, by double layer theory actually, and if I try to do that now, we can calculate the bearing capacity of this reinforced bed actually, and we can also calculate the bearing capacity without the reinforcement. That means just sand only. So if you try to put a ratio of these two things, that means the bearing capacity with reinforcement and bearing capacity without reinforcement, then we find that, for example, for a mesh of 1.4% actually, this value is increasing so significantly. Okay, obviously, the more the higher the h now, that means if h is more, that means 2b, obviously it is very high now. And if the h is going to be less, naturally influence is not much. And if the percentage of this mesh is 0.24%, naturally the value is almost, I think 1.5 or something. This is actually, say 1.5, this is 3. So point is that now, even at a very small percentage, 0.24% now, we do find improvement of the order of 2, 3 like that now, and maximum is around 3 now. So whatever we do basically, in the next case, we have done something different. What did we do? Again, we compared in loose sand condition and dense sand condition now. So what is it you find is that this earlier was loose and now it's dense. So same kind of behavior we are finding actually. Loose condition means it's here, and dense condition is here now. I mentioned this actually. Loose condition, it shows you much better influence, and dense condition shows you less influence. So that is the way in which even theory shows you. And other case we worked out actually is, why not we have geogrid here now? That means same kind of mesh we thought of now. And then calculate by WA theory actually. So this again H over B on the horizontal axis, and this is bearing capacity ratio. And what is it you find now? Based upon increase in H over B now, this improvement can go up to 2.3, 2.4 also. That is the kind of as you suspect. Actually, I told you, this is how the, whatever you are going to place now, it's always going to improve like this. So again, there are a different kind of calculations we have done now based upon the actual results now. Earlier, let us say we placed non-urestyle and urestyle. We did compare them with respect to experiments, with respect to theory. So all these studies were done. They are all published actually very well now. So another way we try to also calculate is using actually granular trench, using the theory initially initiated by Professor Mathur long back actually. We use the same model basically. But now we have, instead of only granular material, we have a reinforced granular material like an interaction test. Okay, this is placed in weak clay. And what is it you are finding is that now same bearing capacity ratio on this side, and A or B means A is diameter of this, diameter of the trench actually, granular trench, and then B is the width of the foundation or load area. So A over B is what we are trying to say. That means A more means obviously A over B is more now up to 2. So unreinforced case is going to give you something like this. And once you place reinforcement, this is going to be increasing. You can see this now, further trench now. So these values are increasing, let us say, from around, I don't know, 7 or something like that, to more than 11 and 12. Same kind of behavior is observing everywhere also. So whatever is the structure we are going to consider, this improvement is going to be must. So then we also calculate actually what is the likely settlement of this. We did all this now. Settlement is not going to change significantly. So when once you do the settlement also, we find that actually the settlement, yes, it does decrease definitely from this value to this value, but definitely not as much as expect now. It's not as dramatic as expect now. For a given case, let us say the thickness reduction is hardly say 15-20 millimeters in a range of 150 millimeters. Here also it is decreasing slightly when H is going to be more because domination is done by the H here reinforced. And we calculate like this for other materials also. So in this case, again, we got a different kind of sand, and we find that slightly more difference. But definitely, it's not decreasing 150 to 50. It's always going to be a very small percentage settlement now. So what is it we want to say out of all these calculations made out based on the fundamental parameter of the clay and based upon the tractional values of the whole thing and based upon double A theory to calculate bearing capacity, we find that it does influence the bearing capacity at least 3 times, 2 up to 3 times, depending upon many factors which are seen. And then the settlement definitely calculated conventionally is not influenced so much now, very much influence is there. It's also shown by a lot of work done by Professor Mantha himself. So then when you keep closely placed also, a lot of work has been done now. It's going to influence a little bit, but not as much as one would expect actually. So for example, in this case now, Das Babu has done 1999. And you see this now, this is the result of the GeoGrid now. Earlier we were all doing with the geo mesh only actually. And you can see value ratio increasing by up to 5 also, depending upon H or B. And the work by Guido and as well as 87 also shows similar kind of result. It all depends upon the kind of sand, the kind of clay you got, the kind of GeoGrid you got now. So influence is very significant in trying to change the bearing capacity. This is definitely taken for granted. So different kind of geogrids again. Influence is more on SS1, one kind of higher, stronger geogrid. Influence is less on weaker geogrid actually. So these are all what I am trying to show you the classical results along with our own students' work actually. So when once they close the space, which I shown earlier now, you find that the group efficiency of many of them now, we find that when n is equal to 6 actually, the influence is felt less. Actually, efficiency comes down. So by placing them so closely, so many of them, it's not going to influence it so much now. And that is what you have to always keep in mind that just because you like having more of them now, but doesn't mean that the benefit is going to be as much. This again is another test result we did really long ago. And this is a classical test. You can say it is a model test in laboratory, of course, done for a different purpose of payment understanding. But look at the way in which results are come out now. So, for example, in this model now, which is of course part of a, you can say, big unit actually, and in this case, the thickness of the silt actually, silt is the soft silt actually, is 270, and then thickness of the, you can say, granular layer is varying from 60 millimeters in one case, 100 millimeters in some case now, and the load, of course, in this case is applied actually over 100 millimeter diameter plate. Okay, actually, this place in a cyclical machine, I am showing the static result only. So when you plot a typical, it's a low test kind of thing. I am showing the pressure applied actually in kilopascal, 100 kilopascals. and the vertical deformation on this. So when once we have no reinforcement at the interface, actually, that means no reinforcement interface now, but or B, that means, for 60 millimeter thickness of this now, we have this kind of curve. The first curve is like this. When you are changing thickness of this granular layer, naturally it's kind of. Okay, I will tell you the best result now. When you place a geogrid here at the interface, the real geogrid, and the thickness of 100 millimeters of this now, we show that this is the kind of behavior. The best behavior. You can see this now, even at deformation of 10 millimeters, we find that there's significant improvement in the bearing pressure. That means, you can see that this improvement is up to, say, 12 or 1300, and this is hardly 500. Okay, if you are changing thickness of this to 60 millimeters, this is what is happening. Okay, again with the different non-ovens, things like that, no, the behavior is there, but then it's not as much significant as the geogrid. Geogrid has been acting perfectly, actually, and that's why a lot of work subsequently we have done with respect to this, and also cyclic loading, and we find that the result modulus improves, and then many things are changing, but then that is not the subject of present topic, actually. So different kind of test result I showed you. One is the traction result, and this model test result now, also done by Professor Bhadas and other people, and conversion of these data actually into some kind of calculations, and all of them show you that there is a significant improvement, at least 2 to 3 times that of the normal bearing capacity. The bearing capacity ratio is going to be obviously at least 2.5 to 3. The one thing which is not mentioned so clearly is that this ratio is going to always improve only when you allow more deformation. Like this also here. Let us say bearing ratio increasing, actually in this case, the pressures can go up to 30, 30,000 kilopascals. Okay, but that's happening only when you are able to sink to 40 to 50 millimeters. It's not possible to do like this. That's why I'm showing you only 10 millimeter deformation. This is it. So with more deformation, that means more vertical settlement, we find that its improvement is going to more and more and more and more. So this also we find significantly, and that's why our students have done a lot of work with respect to even using coir and even using jute also, using all kinds of materials for payment purposes. And definitely they find that the load bearing capacity of this is increasing very significantly, but the increase is more with respect to more and more deformation. If you don't allow much deformation, suppose you see this, I'm only seeing at say 3 millimeter deformation. The improvement is not so much. If you say at 5 millimeter, it's going to much more. So the improvement which you are going to get now is going to be more and more significant as you have more and more deformation. That's why that earlier curve behavior is being shown here now. So the one thing is that this is a permanent arrangement basically. This is not a temporary arrangement now. That means that the strength improvement is going to be followed very, very, very clearly. And as I told you, the success forward pressure generated by the application of the load now, once it dissipates naturally, the solid itself is going to improve and the real bearing capacity improves now. So this is only a temporary phase, you can say this. So this aspect of it has been used by us very well in some of the field studies now. They don't relate to building foundations, but they are very important for us now to understand this phenomena actually. So I will show you this actually. We're talking of high embankments up to 10 meter high, which means a lot more load than what we talk about in normal foundations now. And so this is the same kind of thing I'm trying to show you in a different way. That means as and when you are constructing your embankment on a soft soil, what is going to happen now? We may, let us say, increase the height of the fill to some value. Let me say constructed up to, say, 2 meters, something like that now. So then I stop construction. So as we are constructing, actually, the core pressure also is going to increase. And because we stopped construction now, obviously the same height of the fill is being maintained, so the core pressure will slowly start dissipating. And when the core pressure is increasing like this now, obviously what's going to happen to factor of safety? So during the construction period, as I've shown earlier also, construction period naturally, the factor of safety is going to decrease. Okay, and if you did more construction, that means you increase the height more and more now, naturally it will come to below, it will come to factor of safety 1 only. Because you stop now, slowly, the core pressure is dissipating, so factor of safety is increasing. So that means you have to do slow construction. Slow construction says that core pressure is, they have time for core pressure to dissipate, and this is going to slow the whole process of construction now. We can't afford that to happen now. That's why we said we are going to place a geosynthetic in this. Now, if you construct very fast, actually, obviously, the embankment is going to settled. I mean, remain to fail now. Now, what are the conventional ways in which you can do? You can improve the ground actually. One is you can of course mix some lime. A lot of reports are available with us in the literature. We have done one such study, one such report published by the Indore Congress in the year 2000 actually. And then we can use stone columns. I'm sure it has been covered by Professor Madhav. And then consolidation with sand drains. So that also must have been done now, but these sand drains have got their difficulties. And so we can also use a geosynthetic prefabricated vertical drain which functions exactly in the same way as sand drain actually and behaves perfectly for all of us now, and by which process it becomes if you also because the loading now it becomes accelerated consolidation also. So PVDs are a part of geosynthetic materials, and we are using the functions of both filtration and drainage by designing a PVD. But we don't have time to deal with it now. We will deal with something else. So other way of doing it is that to enable fast construction, we can also use a reinforcement at the interface. That is what we call as a basal reinforcement. Now, what is it we are trying to do? We are always trying to say that it's very capacity improvement. We are actually not doing it with respect to the settlement now. That means these structures either they will be able to tolerate some settlements now. Okay, it is not. That is why we don't say foundation improvement. We always say very capacity improvement. If you want improvement of this of the soil now, it will be drainage systems now, and they will take a long time. On the other hand, now you want to do the faster construction. Actually, we can directly use this reinforcement, and the reinforcement will work till the consolidation occurs. Actually, that is the best way of doing it. And then for this now, we can use a geotextile, we can use a geogrid, and then we can also use actually geocells constructed by using geogrids. That is what we are going to do. This concept has been developed by Tensor Corporation long back. It is part of a British code also now, BS 2006 now. And some of you know that these Indian codes are being now revised by we are trying to bring out a code of practice by the VAS now. And it will actually give you a lot more details of how to use these different kinds of geophysics for constructing what we call as reinforced soil structures. That means reinforced soil walls, reinforced soil slopes, and reinforced soils for basal reinforcement. Okay, so we'll see what is the problem now. What is the way in which we analyze and design, and then of course what are the requirements of the geosynthetics. Okay, and what are the text geosynthetics we already mentioned now, and typical case studies. So it is always a geotechnical problem actually, is it not? We should forget that geosynthetics are going to aid the civil engineer actually, and we have to necessarily follow all the fundamentals which are used in geotechnical engineering, and then of course we go to the next step. Now, for example, we didn't do this kind of calculation clearly. Even normal geotechnical structure also, what is happening now? This embankment actually failed to inbuilt phase. That means your embankment has come down, like what I showed you the first day. Atazaki's concept of the whole thing sinking down actually, and then soil moving out actually. And this is moved out soil. From the base, it's coming out, you can see it's falling on the existing car parts. So these layers are coming out. This is typical bend failure. So this is exactly what we want to prevent. So construction embankments in soft soils, soft ground can lead to deep-seated foundation failure or excessive settlements. No, we're not talk of settlements actually, we talk of how to prevent this kind of failures, deep-seated or shallow, we want to prevent. So this is an excellent illustration, of course, provided by the Intergeological Society, that the whole embankment is coming down and the adjacent soil actually is going up and then falling on. This vehicles like classical failure. So the solution problem now can be done by many ways. Conventionally, we can think of removing the soft material and replacing the quality fill now. Obviously, this practice was possible maybe a decade or two back now. Today, where to put the soil now? We have to carry this soil. And where is better soil now? We are not being allowed to pick up soil inadvertently actually. And because there is a lot of control by environmental authorities to not to really open more quarries and not to transport all these things now. So the question of removing and then replacement is not going to happen now. And displacement of soft material. That means, earlier we used to have some kind of blasting technique actually, by which the soft soil is naturally jumping out, but that causes a lot of other issues of again pollution, things like this. So that is again not a practice which is feasible today. Piling, obviously piling can be done, but that is likely to be more expensive. Then stage construction, that means as I have shown you, You construct a meter or so, allow some time for the power to dissipate, and then keep doing it now. We want to consider 10 meters of 10 meters of height now. Obviously, it will take 10 months also, or maybe more than that also. So, stage construction is not feasible in today's environment, both social and political. Everybody wants to finish structures as well as you can, so that you can use a road or building or structure or a bridge. Then we can have a tow bomb. In the case I illustrated to you, there's no space to construct it because we can't acquire as much land as you think. Because tow bomb requires another land also. So normally, for all we know, the acquisition land has taken place beforehand only. So today we say for safety sake, I want more BOM now, where is the land available? So that also is an issue. Then of course elevated structure. Elevated structure is of course a good option in one way, like our bullet train now, because of the conditions of soil, rock and soil, they decided that the entire 550 kilometers length is going to be elevated only, viaduct only. Obviously, the cost of the entire structure is 4 to 5 times that of the construction embankment. So look at the kind of situation they're going to come now. Elevated structure is a very good option. Piling is a very good option. But then these will be definitely a cost, not necessarily cost effective. The other option could be obviously lightweight fill. That means like we remove the soil and then replace it partly with lightweight. That means like blocks, actually polystyrene blocks, like the thermocol blocks are available now. And part of the fill also we constructed. But in India, we are not start doing it. But abroad also, it has not been done. What you call commonly. Yes, some trials are made. They're successful. But with the you can say prevalence of rodents and things like this, we are not very sure whether this will work in our country or not. And then ground improvement. What kind of ground improvement you can do? Because the kind of soil involved is going to be very deep, very thick actually. So that means something like a stone column can be done. Definitely, very good alternative. Again, in the case I am considering, stones are not available in the nearby and they are not cheap also. So availability of stones is an issue. And PVDs, as I told you, will take more time. So the other alternative which can be thought of is geocentric alternative. So what I'm trying to say is that the engineer in charge or the designer in charge has to look at all the options now. For example, the possible options I am getting into is piling, and then it could be definitely tow bomb, it could be stage construction, it could be some kind of ground improvement, it could be geocentric. So out of these four feasible options now, naturally you have to do some preliminary design, work out the costing, and then decide what is the best now. So just because we succeed in doing a geocentric reinforced embankment, it doesn't mean that it's always going to be there, always going to be correct now. So geocentrics in this case actually are in general provided a structurally sound solution to a lower cost and definitely faster than traditional methods. And in a way, what happens is that now, if the soil, soft soil is trying to move away, it is being held together actually. It is being held back to be underneath the, you can say, the embankment now. That is the beauty of the entire thing. Block is being held back now. So typically it's something like this now. So we have an embankment. In this case, of course, the diagram also is shown. So we can place a number of these layers actually, or one layer, just at the interface, or maybe one or two below in the soft soil, or of course also in the embankment. Now it's up to you. Then we can do the same kind of substitute analysis in trying to do this. Okay, so you would have found out the stability of the slope earlier and found that the factor safety is definitely less than normally 1.25, 1.3 as you desire, and in which case you can place one or more layers of the geocentric and recalculate. Again, study the what you call the factor safety, with typical failure conditions actually, and by number of trials again arrive at the minimum factor safety. So that means in all these cases, we'll of course see what are the conditions which you have to do, but then always there is a slope stability analysis done now. In the simplest way, what is it happening now? If this entire block is going to come out, actually, which is going to come out now, naturally the geogrid or geocentric is going to be here also will be pulled out actually. So if it has got that much resistance between the geocentric and the soil now, that is going to prevent from this one. That means it's going to give you additional tension load here now. So that will be added to the software. So most of the softwares actually are capable of doing this kind of function. We have RISA, which is available actually. We have SlopeW. Many softwares allow you to do this kind of work actually. So again, this I have shown you already. So the kind of things which are going to do will be analyze bend capacity, analyze global stability, analyze deformation, and pull out an anchorage now, lateral spreading. All of them we had analyzed. That means these are going to be exactly the same analysis which you are going to do for normal embankment on soft soil. Mind you, not replacing. This we have seen. So one of the important things before we go further is going to be that in this case, embankment is going to fail actually across the embankment, not along the embankment. So you see in this case, the reinforcement is placed across it. Isn't it? That's why the unrolling is going to be done now. So the geosynthetic we are going to place, we should have more strength in this direction and not in the longitudinal direction. It should be having more strength in the lateral direction or cross direction. That means it will be, if a geogrid, it's going to be uniaxial kind of geogrid and not biaxial kind of thing. Okay. So the high tensile strength required to maintain stability and prevent failure. And as I told you, as the foundation shear stress or strength is increased, the required geostatic tensile force reduces. So that's going to be good for us. So the enhancement of this one is going to be, as mentioned, by the traditional methods only. And solid parameters, initially we always consider total measurements only, total section parameters. So we analyze for rotational stability, lateral sliding, and bearing capacity. So when trying to do this now, as I already mentioned, actually, you can see a typical embankment, and we understand the nature of the software. That means some parameters. We also know that what is the parameters for this, the solve parameters for the embankment now. And one more thing we have to also be very clear, of course, is that usually when you are constructing now, people, the contractors take the salt from the neighborhood only and dump it here. So if he is going to take the salt from around here and dump it now, naturally that becomes a ditch kind of thing in course of monsoon. So the height of this embankment is going to be not this much alone, it's also going to be increasing to this level now. So this is what we have to do. You remember whenever you travel by train in monsoon, all the on either side of the track we have the ditches actually parallel to the track. These are ditches in construction only. So this is one has to avoid this actually. Okay. So once this entire block is supposed to move, or by our analysis of stability, what's going to happen? It is going to be the tension along this now, along this geosynthetic, which is going to come to picture now, and we have way of determining the friction around here now also, what way is developed actually, and then the tension is going to be naturally acting normal to this now, and we take component along and naturally tangential to the assumed failure surface. So all of this is exactly the same thing now. We can use basically modified Bishop's method, it's a similar method, like surfaces, and there are two ways in which you can handle this also. One way is that, yes, the thickness of the soft soil is going to be limited. Another case, thickness is going to be quite large. So the basic theory applies in both cases, but slightly the difference in analysis actually. So then, also what may happen is that blocks at the towards edge now may start slipping away actually. If they are slipping away, naturally, what is preventing it from slipping away? It is only the friction, the interface friction between the geosynthetic and this embankment soil is going to prevent this now. So this can be done. And this is, of course, the active pressure is going to act upon this, so it's going to move away actually. So this is the way it's going to be there. And the friction is cause for the tension being created. So naturally, it is natural resistance which is going to be taken into consideration. A friction, we need to conduct a laboratory test to find out the pull-out value and modified shear value, and then see appropriately what is done. So ultimately, we are only calculating the tensile strength actually, I mean the active pressure, and then seeing whether the friction is going to be sufficient to prevent lateral movement or moving away of the outward movement of this. The other kind of thing which is going to be very critical in the case of relatively small thickness compared to the width of the embankment is going to be, we assume that this is the small thickness now compared to the base actually. So what is going to happen now? It is possible that this entire thing is going to be squeezed out actually. It's going to be squeezed out. So how to prevent this squeezing out is by considering actually a block. By considering a block, let us say. And this block is going to move out again by virtue of the pressure which is going to act upon this now. Okay, and the friction between the clay and this bottom of this geosynthetic now, and the friction between this clay and this firm soil now. So that is why we are trying to minimize the sliding, and then naturally in this entire process now there will be tension developed. That means the tension developed should be developed within the limits of the vertical strain which are going to allow us. That also is going to be important, and that is another way of putting this. It's called boundary exclusion now, and very loosely saying it now, what is happening now? The friction here now is allowing, is making this block stay here now. That means we call it in a loose way. that the block is not being allowed to move, is being tied back to the bottom of the embankment. That's called extrusion prevention. So that is a beautiful concept which is developed by the Tensor Corporation, and based upon the work done by them, theoretical work, and also a lot of field studies. Uh, Naturally, we have ways of analyzing this distribution of the stress because of all these forces actually. So we know that once there is a geosynthetic is placed, and then we say geocells also, the kind of stress distribution is going to change. So that change in stress distribution, because we reinforce the entire area here, is going to be is made in detail in the British code, and which we followed in the case study which we have done as we go further. So then, of course, susceptibility limit. Uh, we need to consider how much settlement is going to occur, and can we allow this or not now? Obviously, this is a question which the client has to address. So when we are providing these instructions now, we are going to say that we are not going to control the settlement, and we calculate settlement almost in the same usual way, and indicate to the client, yes, this is what is going to happen. So requirement of the geosynthetic can be definitely high tensile strength in the roll direction, ability to carry load for several years, that means still the consolidation is going over, and then ability to transfer the load from soil to geosynthetic by friction if it's geotextile only, and then by interlock if it is going to be geogrid. So these are two things that are going to be there. And then, of course, it should not be damaged during construction. So that also we have to consider in determining the allowable tensile strength of the material. And then during construction, obviously, it should not be exposed too long now. Sometimes, there are construction issues between the client and contractor. And so if it is exposed too long now, there is a problem of degradation of the geosynthetic also. So in which case, you have to protect it. That's all what we have to do. And the materials we are looking at are going to be either high density polyethylene or, of course, the polyester. And in both cases, naturally, these are not degradable from biological viewpoint. So that is what we have to keep in mind. So the common kind of material could be what we call as woven geotextile. Knitted geotextile means it's kind of geocomposite, wherein there are fibers of woven fibers of polyester knitted onto geotextile. So it's a composite, means there is also drainage possibility because these are knitted on the non-woven geotextile. So either the pure woven geotextile or it's going to be the knitted geotextile, the woven on which we have the strands of polyester, or of course a gasket in high cases going to be done by knitting process actually. And mind you, the strength of this sometimes can be as large as 1250 kilonewton meter. Though in our country we use up to 300 only, but this thing is available actually. And extruded grids, which I am going to show in a big way. And then there are also welded grids that are possible. So these are what is there in this case. So the first experience outside the country in the beginning, long back, maybe 2-3 decades back now, the embankment constructed over swamps and fish pond, soft clay foundations, 10-meter deep, strength as low as 3 kilopascals. Mind you this. The thickness is 10 meters and the strength could be in some locations as low as 3 kilopascals. So in this case now, we place a geotextile here actually and avoid a need for long preload or replacement of soils. And they have driven actually band trains. PBTs have driven actually before placement of that. And so that way they also measure the settlement, measure bore pressure, lateral displacements, and this allowed them to do faster. But we know very well this is very good technology. We need to spend extra time actually, extra time and money also, and allow full consolidation to occur. And this, of course, practice of using this kind of technology has been done also in Visakhapatnam Port, Visakhapatnam Port Country area, airport as well as Port Country area. But then sometimes time is allowed for construction to occur now. On that, of course, they use the textiles for airport and many other kind of materials for the Port Country project in Visakhapatnam. So then after that is done, of course, we can always have, obviously, in this case, a unidirectional grid placed across the material. So in this case now, the strength of the material is not as poor now. The soft soil is 6 meter thick, and then the strength of the soil is definitely much better than the earlier one, 10 kilopascals, 20 kilopascals. So mind you, when the strength is so low, up to 5 kilopascals or 3 kilopascals, naturally they have to also resort to the PVDs, a drainage system also, because once you start constructing now, the soil is so soft there is a squeeze out also. That means you can't construct fast now. So to prevent all the things now, they did use a PVD for some time, and then of course started constructing using a geotextile as a reinforcement. But when the strength is definitely slightly higher than the reasonable load, not very low but low, then of course we can directly start constructing on this by using the geogrid section. So the geogrids will tell how exactly to be done actually, and what kind of is it geogrid only or is anything else. So then the development which has taken place originated by the Tensor Corporation, and then which is now part of the British Code. Now the reports also is that we get a mattress actually. We call it a basal mattress. Okay, so this basal mattress, of course, can be placed within the soil, within soft soil, or can be placed as part of the beginning of the embankment itself now. So the provision of geosol mattress actually will cause a change in the what you call bearing pressure of this entire embankment on the soft soil now. By the process now, we find that the center portion is going to be still having maximum load capacity, sides will be still active, but then the entire thing is not allowed to move outside. That is what is going to happen now. It becomes that when the soil is going to reach the plastic condition, the geocell is going to come into picture now. You see this now. Normally in a bearing capacity system now, in a hypothetical at least you calculate the aggregate bearing capacity and divide by factor of safety and get a say allowable or whatever you want to call it now, say bearing capacity. In this case now, we can allow the soil to go to ultimate condition, but then the improvement is coming to make it work only under, let's say, safe bearing capacity because of the presence of the geocell mattress or earlier geogrids. So let us see what this really means by an actual example now. So now we move over to Vasistha River, Vasistha Godavari. On the left hand side is a village called Chinchinada, that means towards Palakal. And this side is called Dindi, village called Dindi. This is towards Amalapuram side actually. This is Vasistha Godavari River. You can see this, the sea is obviously Bay of Bengal is about maybe 5-6 kilometers away, and water is definitely salt. So when you look at Vijayawada side, or when you look at West Bengal side, the road can go to Vijayawada actually, and this side is going to Rajahmundry, and the bridge proper is going to be 1200 meters long actually, and the rest of things we will try to see. They're not so much important, but we'll see what are the conditions. So the approaches on the West Bengal side, the height embankment is approach embankment is 10.5 meters, and on the East Bengal side, it is actually 12 meters. The Indi side is 12 meters. And you see the kind of strength of the soil actually. The strength of the soil is definitely quite low for taking up the 10 to 12 meter high embankment now. This is only C value is 17.5 here now. And here also it is up to sometimes 12 only. And maybe 30 here, maybe 21 here now. And angular friction is also very small. But mind you, this entire thing is actually black on soil up to 22 meters actually. So on such a material actually, which is called low strength, we are going to construct embankment of 10 to 12 meters. One funny thing is actually, this is not continuously only black soil. There is also lenses of sand available now. That means the sand could be there at this depth in this borehole, and other borehole, the sand could be somewhere here now. They are not connected sand layers actually. So that is what we have to keep in mind. But so some support also probably was coming from sand, but they are not continuous. So there is no drainage capacity for them now because there are no lenses actually. Okay. So it is a 22 meters of soft clay, black and soil kind of soil. And then we got very low soft, very low strength basically, and on which we want to consider high embankment angle. So for this now, so what is it we have got? As I said, high thickness of black on soil, the embankment maximum is 12.4 meter high. So we decided to go for a basal geosol mattress, and then naturally for safety now we wanted to have a, you can say, a ledge also, a berm also, but then that much is not possible. So what is going to happen now in this case? Actually, we have to cut this edge portion and elevate it by constructing a reinforced soil wall. So we'll see all that very clearly. And normally, such an embankment will require erosion control blanket, erosion control systems, and pitching was what was thought in those days now. But then instead of pitching, which was costing 120 rupees per square meter, we use actually material which is what we call as rolled erosion control blanket (RECB), which was costing them in those days only 40 rupees per square meter. We can see how actually work now. So the alternatives are, we already thought of all the alternatives now. I will not discuss much on this. The one thing which you can see is that the geocells actually are made in a very different way. So using basically the uniaxial kind of geogrid now, They are directly placed on the subgrade, but instead of the directly subgrade, we use a biaxial geogrid initially, and then construct the cells actually using uniaxial kind of geogrids by using naturally transfer diaphragms. We'll see how exactly that's done very quickly. And by doing all that, we get actually triangular cells now. So let us see what is done now. This is the finished structure basically. We'll come back on this again. I think that is, we'll come back on this again. Yeah. So you see this now. We'll start with this. Yeah, you just see this very easy to understand. First, we place a geotextile, we got separator now. On this, we have got a biaxial geogrid. Then we have these geo grids, universal kind of geogrids now. These were actually laced together to the bottom. So like that, at the regular intervals now, they were laced together now. And then these were held vertically. And then a diaphragm is stitched between these things. The diaphragm stitching is done again by lacing, interlacing. And that is done by Botkin joint actually. So what did I show? Initially, this was stitched, laced together by plastic rope. Another one plastic rope. Then these are appended, made vertical. And the diaphragm is going to come again in the same form of uniaxial geogrid, but then this is tied together actually by using a Botkin joint. Botkin joint actually is 100% strength joint actually. You can see plan view of this. This is a joint Botkin. That means you can say plastic rod or a plastic pipe or plastic strip actually very strong. And this joint actually is 100% efficient. That means there is no loss of strength at all. So Botkin joint was a very simple but effective innovation actually done by this company. And we are able to construct these structures like this. We'll go back on the entire thing. So by using these cells now, construct like this, we'll see what is going to happen now. So in this case, we constructed cells of 1 meter and half meter thickness. And as I told you, this was the way in which is there. So we need to also have our foundation beyond the edge of the embankment. And that is to prevent extrusion at the edges actually. And for that now, we need actually a special enrichment. That means we have to construct also a deeper foundation than the basic cell. We'll see that also. That is what is done now. In this case, this is 1 meter high diaphragm and 1 meter high geocell. And at the edges actually, we have the end restraint by creating under 1 meter deep and 4 meter wide cell actually. So these two are end restraints and this is a regular one now. And what I mentioned was this entire embankment should have been going up to this actually. In the pictures, you are going to see that we don't have inch of land available actually. This is only service road now. So all along here on both sides is going to be an excellent paddy farm, and also of course is a coconut grove basically. So they are not going to give an inch of land, and also the point is all black cotton soil. Water table is at the top now, and paddy cultivation also requires a lot of water anyway. So we are going to consider on this kind of area, and this section basically of course taken from the standards by the set up by the then Minister of Surface Transport. All the slopes and all were taken like that, and analysis done as per the conditions which I mentioned now. So on the 12-meter high embankment on the Dindi side, what's happening now? We made the geocell. The basic mattress was 1 meter thick now, up to 8 meter height, and then beyond that, of course, it's going to be less thick, half meter thick now. And for height up to 10 meters, we had this end external mattress also, and then this also was there, much less thick now. And then afterwards, we placed only a geotextile actually. So because of the requirement of the wall actually, that was required only at of course up to heights of I think 5 meters, and beyond that we require that wall. So this is an normal embankment only. So beyond 5 meters, below 5 meters is an embankment, and then this is a wall on all the sides up to 5 meter height. So all the details worked out now. This is the initial site. You can see this now. This is the abutment is going to come over here now. And you can see there are paths which are there now, cattle is grazing now, there are pipelines below this now. And we are going to work on this area. As I said, there are paddy fields now, coconut groves and things like this. Very difficult to work because it's not like uniform site, labeled for inauguration by Shankustapana by somebody. So the point is that it is not really the kind of land we are going to expect. We are just going to level it and start constructing on this. Absolutely no other foundation. And by the small drain they construct actually, culvert kind of thing. And you see this kind of soil now, really pitch black, how soft it is, you can imagine. It's like a black gold actually. So then, of course, it was leveled and then this geotextile place now, I mentioned how to do this now. And after having placement now, so they were actually also pulled out on a small, you can say, vertical members actually, otherwise they will lose. So they have to be pre-tensioned, you can say. These cells are formed like this now. And then the question of filling comes in now. So we can't fill arbitrarily now. We start filling the first two ones equal height now, and then this is filled up. First cell is filled up to the top now, and by the time this is done now, this also is filled to the half now, and then slowly we move. Actually, you keep filling adjacent one to the top and the next one to the half. So there's a way in which you have to go across actually, not simply at random, because the tension has to be uniform now. So what is done is this filling can be done by manual labor or can be done by machines also. We are no worry at all on this now. And when place is going to lose only, so what did we do? We place this to whenever the thickness is 1 meter, we place up to 110 centimeters, and then of course we place the geogrid on this, and then it was rolled also. So after rolling now, it can come down to compact thickness is going to be 100 millimeters, which is the height of the cell. So that is what is done now. Again, as a separator, we are cutting up with geotest cell, and the rest of the construction can take place as usual. And this foundation pit, which is drawn for the wall, the foundation of the wall actually is done like this. So we can see this construction of the round bumps now, and we can see this side wall also here actually, and construction will be done as usual. So when the trench is dug for the wall actually, you can see what is almost near the surface only. So that is something we have to keep in mind. So then we made the initial concrete trench kind of thing now. Then the panels for the wall are made actually, and then they were start erecting on this now. Then the construction proceeds as usual. Mind you, all this is designed by ab initio. Is the first kind of wall or first kind of structures that is placed on such as kind of soil. The contractor was not experienced in doing it. He was enthusiastic, all right, but then we had to go and supervise. I used to come regularly from Delhi, at least every 2 weeks, once in 2 weeks, weekends, uh, naturally accompanied by the engineers, Mr. Jashan Kumar from Hyderabad. We used to travel together to Palkola, Bhimavaram, and then start traveling. We had to really exert also in order that the structure becomes very strong. Actually. So this is how the construction is going on, and we can see rolling is not an issue now, curvature is not an issue. So all of it is going to be done like this. So this is almost a finished structure, you can say. The slope is finished basically. And then, as I said, instead of placing the pitching, stone pitching actually, we initially placed the black on soil. The embankment soil is not black on soil. Embankment soil, silty sand. So the local black on soil is placed on this now and weeded, and then it was covered with the road erosion control blanket, as I mentioned now, essentially coir, and a very special product now. Today, 3-4 companies in India are making actually, and this is spread over this and then anchored actually by pins, and then we place naturally the seedlings of turfing or grass, and slowly, within a month, the grass started growing, and then we see by the beginning of monsoon, it is green completely. And in fact, it is so beautifully now also. This is open to traffic around 2000 actually, 2000, 2001 or something like that now. And so naturally, the first major work we have done, and based upon this concept, other things also were done. But the point is that now this gives confidence that we can work on the local soil, we can work on background soils, we can make the geoshells, which are done for the first time in the country, and along with that, we could also make a small wall actually within the limited space. Only this service road is available. You can see the plantation or the paddy fields adjacent to that now. And another important point I want to mention also that during the course of construction and even 10 years also, the total thickness of the settlement was expected to be 1.47 meters. So this much settlement is going to occur at maximum height anyway. So that means the embankment is settling definitely, and you can see the patchwork also. So what is it we do? We don't place the final finish layer actually in the top now. We only place the BM kind of, bitumen macadam kind of thing. And after 10 years, I think they place the DBM and then BC. That means dense macadam and concrete on this now. So till then, naturally, they were doing some works for the pavement now. Otherwise, the structure is perfectly intact. So that is one thing we have to see. On the other side, also we can see picture now. It's a beautiful. This is the abutment portion actually, and this, just behind this is the obviously the river. And then we of course vehicle stop here, but this becomes a picking spot in good season actually. In Kartik Mas people do it. So the advantage for this is going to be no excavation and minimal site preparation. No trips required for disposal of unsuitable expert material. No difficulty working at or below the water table. So this is something going to be very important actually. The only thing which I remember, of course, is we require initial training to familiarize the workforce with construction initially, and supervision strict pattern of working is required. The engineer has to be there inside. And in order to maintain the rigidity of the mattress during construction and infilling, a large degree of transitioning of the transverse vertical diaphragms is necessary. We have to pull them up and then tie it to the pole actually. So that is there now. So using this concept now, I will quickly run through this now. At a site very nearby, that means upstream of the place I have shown you, both in the Sista and Gotana River, actually there are two more bridges being built in those days now. And that means four abutments are constructed, four bridges are constructed now on three approaches actually. They did a similar kind of thing, not same kind of thing. Here, the black console was 4 kilometers thick now, and the kind of structure which was designed actually was something like this now. Here, the green one is the foundation I'm going to say, and here is a wall also going up to even 10-meter height actually. And this was made like a reinforced slope basically, and this is partial slope loading on this now. So a lot of since the work was done, the materials which is used from Whisker actually they did the design, but then I vetted or have helped them in a lot in doing the detailing actually for different things. So this is the way what is done now. You can see uh, the ledges which are made because that will reduce the length required for the reinforcement. And you can see this is the reinforced zone. I will show you the reinforced zone actually, reinforced, you can say mattress you can think of now, but done in different way. I'll show you what is that now. You can see, the geotextile place again, same understandment at both sides now, and geotextile being placed actually. This is being filled with the sand, local sand that means from the river. They place coarse sand, and step by step procedure of construction is followed now. You can see the kind of strength of this. It could be 200 kN kind of strength actually, and the other direction naturally it is 40 kN. And this is how the construction is done. Happily, the construction is undertaken by the L&D, the design vetting by IIT. And with all this now, this construction was feasible. And at the end of the day, you can see this structure now. This structure is being covered actually by using concrete planks. That means, unlike a normal wall wherein the reinforcement is tagged or connected to the panel actually, here these are separate from the vertical slope actually. These are only stanchions, high girders actually, and these panels are placed. Okay, and you can see the curvature very beautifully. I mean, it's 20 years since construction, and curvature is there now, and this is main bridge portion now, and nothing happened to this, despite the settlements and all. Nothing happened to this entire thing. Probably settlement occurred during construction only, and it's done by L&T as I mentioned to you. And using these concepts now, locally also people started using this in both East Kerala and West Kerala for different distance now. Obviously, they don't have to come to IIT for this now. And even on canal roads, actually, there are a lot of problems which are there. And they are building these small walls, small height walls within the canal bank, actually, like this, so that it prevents further damage of the so-called road, which is again totally black on soil. And there are success stories which are built by the same concept, actually. And naturally, our road width has increased now. They are more stable now. And such structures have come up in the, you can say, MP Road in West Godavari near Martyr, and here Mandapeta Road in East Godavari district now. So people have accepted that the technology works very well now, and there is little damage to the main roads actually. So what is it? Summary of the entire thing is going to be: experience has been gained in design and construction of reinforced embankments on soft blackened soils as per the standards now. The point we are trying to say is that these structures have tolerated the settlements. Okay, that is the main thing now. If you think that the settlement is going to be important now, naturally the option for you will be like one of the cases I mentioned is going to be providing a drain now, which means additional cost now, and you have to wait for the construction to occur now. So that is the main thing now. Whereas provision of a reinforcement is almost indirectly like your stone column at a much lower cost basically. And in a stone column, naturally you get the strength and hardly any settlement. But in this kind of LTS improvement, it is not going to be giving you the settlement reduction. Yes, some reduction will be there. Different settlement will reduce now. But then we are not doing this, doing the placement of the geosol mattress for reduction of settlement. It's only for allowing construction fast rate and ensuring uniformity in the structure and tolerating the settlement. These are the important to us now. So what is most important is that geosynthetic material evaluation and geotechnical calculation is must important. They are simple to construct, even in difficult terrain, and can provide alternative economical solutions in a wide range of applications. So as I mentioned now, if anyone is interested in looking at the entire range of application geostatistics and the types of materials and other things now, as mentioned by Professor Satyanarayana Garu. You have to go back to iGrid site and you can watch all the videos which are free. You can free download also probably. You can watch them and then come back to me for any doubts. I just wanted to give you an overview of this kind of thing now. And this may not fall into the basic category of basic foundations, but we should remember that foundation doesn't mean that it's foundation of only a building. It is foundation of actually all kind of structures. And with the emphasis which are being given by the government of India and state governments on infrastructure development, particularly road infrastructure now, I think you know that the plans of the central government is to use, I think, 111 lakh crores in the next 4 years to build a better infrastructure. And most of it is essentially on road infrastructure. So for road infrastructure, we can improve the road condition, road improvement, and also the approaches and other things now. And some of these sites actually are greenfield sites. So when the greenfield project now, that means you can go through soft soils, it will go through swampy soils, it will go through useless soils now, and geoscience actually play a very important role in construction in those areas now, and it gives confidence to this now, and probably in the short time, in the next 2-3 months now, probably we'll be able to make out the code of practice also. It gives us confidence in the use of using the systems now. And lastly, the most important thing for all of us is that when we began the work of geoscience in '85, naturally we had absolutely no inkling of manufacturing in the country. Today, almost all the kind of geoscience are being manufactured in the country. In fact, till the COVID business has come, before that they were exporting probably extensively, even 40 to 60% of the production is being exported. That is the system now. So you have world-class materials which are there already in the country. You can go and see them, you can go and get tested, and then you can also design using this now, either using the available our Bureau of Indian Standards codes or using the Indian Road Congress codes. And as I told you, we are going to shortly submit to the BAS our version of the geoscience for soil structures, in which this kind of application is also going to mention. And with that, it will give us confidence in trying to use it. So I wanted to show you the theory and some sense of why it works now, what are the limitations, and one application. We have many applications which I've done on such soft soils, wherein the criticality of construction and safety is always important. So I thought I'd just give you some overview of the entire thing. Once again, I thank all of you for your patient hearing, and then Professor Satyanarayana Garu and his team for making this not only my lecture, but also all the entire faculty development program we conducted very excellently, and I'm really grateful to him for having given the opportunity. And it's always a pleasure to work with Andhra University and colleagues like Professor Reddy in, you can say, in extending and widening our knowledge to our co-teachers and practitioners. Thank you very much. Namaskar.
Thank you, sir. Now we'll take few questions from the participants, sir.
Yeah.
Shaker, you can unmute yourself and raise your query.
Hello, sir. Good evening.
Good evening.
Whenever we are constructing a shallow foundation and we are using GeoGrid below it, if we are not getting the settlement criteria, then what is the other method to get that settlement criteria? Means to minimize our settlements.
No, it depends upon how deep the soft soil is. It depends upon how thick the soft soil is, actually, is it not?
Yes, sir.
The thickness of soft soil is, let us say, relatively shallow, 1 or 2 meters now. We can stabilize in the normal way. You can do lime stabilization, cement stabilization, lime flash and all. Basically, chemical stabilization, you can say that. If it is going to be deeper, again, we can follow by lime columns or by, you can say, other kind of methods. Okay. Lastly, of course, we can improve the, see, it all depends on the project which you are looking at now. I mentioned PVDs kind of thing. I mentioned sand drains. We mentioned stone columns now. So it all depends upon many things now. We have got methods of doing it now. But I don't want to restrict myself to normal foundation, because normal foundation is a very simple structure. Mostly people are trying to replace, let us say, if you expect the depth is 2 meters now, I replace under 500 millimeters by sand. That is the age-old technique. We can still follow that now. But what about settlement now? And also, I would like to distinguish between the settlement which occurs during construction and settlement which occurs after construction. isn't it? So if it is shallow, we got different methods. If it is deep, there are different methods now. You remember I mentioned the allowable settlements also. If it is sand, it's different kind of system. It's quite different kind of system. We can't say that you just follow this now, because you have to understand the whole range of issues connected with ground improvement. It's a subject by itself now. Okay, there's no one method for doing it. The methods actually could be, as you already know, which are taught probably in the initial lectures by, let us say, replacing part of the soil now by having different size shape footings now, or we can think of sometimes crowd foundations. Okay, there are many options for you actually. So it's very difficult to say without any data, because always going to be site specific actually. And today we are not really talking of what we think of a conventional kind of systems. As I told in the beginning also, we're not looking at the Tazar's equation for minute capacity and Tazar's equation for settlement now. They are very elementary kind of thing now. I mean, you do by Excel sheet only. We are looking at project site, then options becoming relevant to us now, and selection also becomes relevant. So you should see what are the options available to you to begin with now, and what is feasible basically, and then also the cost aspect of it. That is something which is an advanced level of working is going to be like this. So I do not work on only increase the width, increase the depth, increase this, increase the shape. Oh, we are going to reduce by 75 because you remember this. I mentioned this in my third lecture that the capital settlement is only very elementary. The actual settlement occurring could be much higher and much lower than what you are predicting. If you really want to do that, you need instrumentation. You need a very thorough sampling also. Many things are there before the cup and the lip is, as I said. Okay? So don't look for a simple solution for this kind of things. It all depends on big projects or big areas which are looking at now. Then you consider the options I mentioned at the beginning now. So we have to pick up one or two, three options, calculate what is the costing and things like that, what is the time, material available, technology, and many things now, and then come to a decision. That's the way. That is being done in the country. It's not anymore theoretical like this. It has to be done. There's no other way. For example, from IT Gandhinagar, we have been asked to find out how we can construct, let's say, airport in an area called Dholera. Dholera Airport, and new township is going to come there. The submerged for now last 6 months actually. That means the site is below the sea level, you can say that, more or less, in a way. Then what kind of thing you are going to, what institution is going to do, what improvement you are going to do, very difficult to say that. You can say any one of them. Even the field of, even the, what you call, borrow area also is not available actually. And then we are going to have runway on this now. We are going to have ATC on that now. So these are the challenges which we are going to encounter. Okay. And merely my saying that use lime, use flash, and use this, that also we have done. But to say, to pinpoint what this is solution depends upon many, many things which we may not even know actually. So that's why we have to go through the, as part of it, I think Professor Reddy also agreed that if an SC event is going to be there, it will be on ground improvement measures actually, which are practical by so many cases which I have got in the country. We got enough experience on this kind of thing, and naturally it is worth sharing those things.
Sir, we have a few more questions from Jayashree.
Yeah.
I think she can pose the query to you. Jayashree, kindly unmute and raise your queries.
Hello, good evening, sir.
Yeah, good evening.
Sir, I have done geogrid reinforced shallow foundation analysis of clay and sand in Plaxis, sir. I want to validate from analytical equations, sir, but I can't found, sir.
I can't give any answer for that, but you look at my book, I know, wherein Sridharan has worked out how to calculate these conditions actually. But I don't understand why you want to do that. Again, I'm telling you. The
Okay.
question which addressed to me, first question, you should understand why is there is a question. Are we going to get the parameters or access actually praxis by using all these things now? Why you want to look for a close solution? Why do you want to compare this? It's good you compare it. You get some equation. What is good of this now? You want to say that I can use this now? How to specify geogrid actually for your solution? Have you got
Sir,
shear models for that now? No, these questions I'm asking you. It's not that I'm questioning you. These questions arise out of any such solution. So these are what, in my opinion, are all actually very primitive kind of attempt to understand this.
Okay.
And you don't get anything by doing pure research on that now. You have to conduct actual tests now. Full-scale model studies.
Okay, sir.
That will give you some idea. And then I just now mentioned that it's not a solution for bearing capacity of a normal foundation. Isn't it? Simple foundation. So please remember that now. One is doing some project and getting good paper or something is one different thing. I think very recently only a lot of things are coming up now. The academicians have to look at the practice of the system. You are looking at normal teaching. We means academician looking at normal teaching and research and some source service. But more importantly, it has to be practice has to be the most important thing. How we are going to change practice? Supposing people in Guntur, let us say, they should think what is the changes they can do in foundation back on soil. They can spend whole life on that now. Isn't it? So now testing black on soil and giving current solution is not the end of it. They're just the beginning of it now. If the colleges, which are so many there in Guntur, 20 of them are there, if they are unable to come to understanding on what is the most effective way of using modern materials or modern technological improvement, then what is the use of that now? I'm sure there are a lot of papers. I'm sure they are doing very well. I'm sure they are knowledgeable. I'm not questioning that. But have you come to any solution for the kind of issues you have got in the erstwhile Amravati or in Guntur district? So I'm looking at that kind of thing in backhand source, let us say. Maybe I don't know what area you're looking at now. If you look at some model where the praxis or analytical solution, where are you looking at solution in the end of praxis now? If you think that analytical solution is more important, you should have analytical solution only. Why then you why do it praxis now? So as an old man, I get to these questions actually. I look at fundamentally what is it you're trying to look at now? Your whole aim in life is going to be compare praxis solution with the analytical solution. What is it we are going to get by doing this now? Are you going to get design system for that now? Isn't it? Can you develop a design by doing analytical solution and the praxis now? Can you develop more understanding on this? Can you develop parameters which are required for doing praxis analysis, or we assume some parameters now? In what way, let's say, policy grids and PP grids or HB grids are going to behave in this manner now? Or if you think geotexture, what's going to happen now? Like Professor Reddy said, we are with geocomposites in our case. Are they going to behave well or not? What is the effect of size? So what I'm saying is that you understand by applying a system, applying for a problem, praxis. But somehow that can't be end of it. That's just the beginning of it. Unless you go further than this now, the utility of this practice is going to be limited. That's why you find that most of the local institutions throughout the country, they're teaching well, no problem at all. But then the local engineers are not getting benefit by that. Because solutions are given by them are the same thing you have been given last 20, 30 years actually. You talk of Kerala, talk of any other state, everywhere it's like that. Because we're not looking at the practice subject now. We are just going with the conventional engineering. So what we have been taught to us in this particular program is, of course, essentially conventional. How to optimize systems. I'm not blaming anything because first we have to do conventional only. But then the last two lectures should have given you, opened your eyes now. There are different ways of doing it now. Can I do this now? Now suppose to a friend earlier, I just mentioned that we can use lime stabilization. Now, how much percentage of lime we are going to use? How are we going to mix it now? Is miscible in clay or not now? Should we do it OMC or not now? How to bring the soil to OMC? In what layers are going to come back? How to find out how to find the strength of that now? How much curing we are going to do? 100 things I'm going to get. For me, very easy to say that do lime and cement or patch anything else. But to be practical now, I do 100 things before I say that do this stabilization. So solutions we are getting from most of the, I should say academics, are like that only. Do lime stabilization. Or add 5% of this or that. Now, how to go about this is not what is being. Somebody wants to ask something?
Sir,
Anybody else?
to add to Professor G.V. Rao's comments,
Yeah.
JSP, you can as well refer to Binkett and Lee, right? Theory for estimating bearing capacity of footings, right? Supported on reinforced soil beds, right? Reinforced with layers of geogrid are high tensile strength, high stiffness geotextiles. So you can also go through Binkett and Lee analysis. So that enables you to theoretically estimate, right, the supporting strength of reinforced soil bed.
No, these are given, I told you, by Procedure in my book, first book in physics, Procedure has a chapter on this now. How to calculate, he has given equations for that. This is what I mentioned to her. After
Thank
having said that, I said, what is the use of this? I'm just going beyond what she asked actually. Okay, this is there. Same theory he used actually and described the problem very effectively. And afterwards, they are also not following it. That is the point I'm saying now.
That is true.
For actually problem now, they are not necessarily following it. We got good theory. We all, the Bible for foundation improvement is always, bank basis only, Binkett and Lee. There is no doubt on that now. Anyway, in the early days, probably 85, 90 when we published the first book, now actually he kindly wrote a chapter on my request, and that is still valid.
Any more queries? So, if there are no queries, on behalf of Department of Civil Engineering, Andhra University College of Engineering, and on my own behalf, I thank you very much, sir, for accepting our request to be the main resource person for this faculty development program, and for delivering highly informative and useful lectures with a number of case studies, particularly today's session, wherein you have covered the application of geocentrics for bearing capacity improvement. So not only you have covered the conventional building foundations, more interestingly, the application of geocentrics will be used to strengthen the soils subgrades, right, which will support high embankments or embankments on soft soils. So that aspect you have clearly presented with case studies, and also the improved shear parameters, that is bearing capacity ratio, how it is improving, that also have explained with the help of laboratory tests by conducting tests on samples with multiple layers of reinforcement. So this has certainly has given enough insight into the subject for the participants to think forward and choose some problems and to think about application part of it in their profession. So thank you very much, sir, for sparing your valuable time.
Thank you. Thank you.
Very highly informative. So thank you very much.
It's always a pleasure. Thank you very much, sir. Namaskar.
I thank all the participants for actively participating in this 2-week-long faculty development program. So even in the last lecture, right, the number of participants, right, it has crossed 50. It shows, right, how much interest, right, they have, and how they were involving in the sessions of the faculty development program. So last day is much more important. As per AICTE regulations, right, all the participants have to take a test and score at least 60% of right the marks. So tomorrow morning at 9 o'clock there will be a test. There will be 20 multiple choice questions and 10 true or false questions based on the topics that are covered during the faculty development program. Right. So I request all of you to be in time so that by 9:30 you can finish taking the test, and then we will discuss on the questions of the test and any other queries raised by the participants. And in the evening, we will have a valedictory function of short duration of about 30 to 45 minutes, wherein right, mainly we'll focus on your feedback, and we'll collect your feedback through feedback forms. Right, so don't miss out for tomorrow's sessions. They are right as important as the sessions you have been attending till then. So once again, I thank you all for taking interest in FDP organized by us. I hope, right, all of you might have got right enrich your knowledge in the area of right foundations and how to improve right bearing capacity of weak soils possessing low bearing capacity, and how to tackle right the foundation problems in problematic soil like expansive soil and all. So thank you very much for your patience. So some days those sessions went beyond the scheduled times, right? Most of you stayed back and right paid your attention and raised appropriate queries, right? By the way of posing questions, not only you got your doubts clarified, you have right made it things more understandable to other participants as well, right? So I congratulate all of you for successfully completing right 11 days, right, technical sessions of FDP, right? So relax tonight and tomorrow morning join at 9 a.m. to take the test, right? So even if you miss some sessions, always right they are available on YouTube using the links, right? Leisurely you can go through the lectures, right? And you can also share the links, YouTube links to your students, both UG and PG, so that they will also get some additional knowledge to what they study during their UG and right PG study, right? So you can share the links to them. So thank you all once again. So we'll close the meeting for now and again join back tomorrow at 9 a.m. So before leaving, right, kindly fill in the attendance, right, form and submit. So in multiple choice questions also, only one right answer will be there, right? So need not think too much, right? Only one correct answer will be given.